let me summarize what we had so far in the course. We talked about geometry of ket-zero cube complexes, and we discussed how to cubulate groups, so finding group actions on cube complexes. And then Danny explained to us how much good information this gives on the group if we know that the cube complex is special. Okay, and in particular, you get that the group is residually finite. Right? That's one point that Danny emphasized. And this talk is, in a sense, a bit unrelated to the first two in my mini course, and is sort of the opposite to Danny's talk, in the sense that we'll try to build groups that are still cubulated, but non-residually finite, and this was done by Danny. But also construct such groups that are simple. And this was done by Burger and Moses. Okay, so is the goal clear? We want to construct simple groups, just means the no non-trivial normal subgroups. Yeah? And the way we'll do it is we'll use products of trees and maybe other spaces. But let me give you the general strategy or recipe to find a group that is simple in this context. So so the goal would be to find a group that's first non-residually finite. So let me remind you what this means. This means that the intersection, so residually finite, if the intersection of all finite index subgroups is trivial. Okay, so non-residually finite is that it's not trivial. Okay, good. And then the second ingredient would be to show that this group is what's called just infinite, or in fact that every finite index subgroup is just infinite. So just infinite. Which means that it has only finite quotients, except for, of course, the trivial. So every normal subgroup in G is either trivial or finite index. Okay. And let's see that if G satisfies those two properties, then G, well, maybe G is not itself simple, but has a finite index subgroup which is simple. Okay, so it's a very simple algebraic proof. You take this intersection of all the finite index subgroups, that's the finite residue. Okay, and you consider this. This is naturally a normal subgroup of G, right? Because if you conjugate it, it's like conjugating those finite index subgroups, and they're all finite index. So this is normal in G, okay? But G is non-residually finite, so this is some non-trivial, so FR, let's put it there. It's non-trivial because G is not residually finite. Okay, so since G is just infinite, it must have finite index itself, right? So this finite residue has finite index in G.
That's the just infinite.
Yes.
It's true for every subgroup, so it's true for the whole group. That's what you're using now, right?
Yes, it's true for every finite index subgroup. Yeah.
Yeah, so it's true.
Okay, now what? So I want to claim that this subgroup is my simple group, okay? So it has finite index, hence it is just infinite itself. So that's the assumption. And what kind of finite index subgroups does it have? Well, it has none, right? Because any finite index subgroup of a finite index subgroup is again finite index. Yeah, so this finite residue was finite index, any finite index of itself must be somehow contained already in the intersection. And so this guy has no finite index subgroups. Oops. No finite index subgroups, but also no non-trivial infinite index subgroups, because it is just infinite. So, infinite index normal subgroups, sorry. And so it is simple. Are we happy with this very elementary kind of group theory idea? Of course, the difficulty would be to somehow find an example in which those two properties somehow happen together, because they're kind of...
The just infinite condition sounds very strong.
Yes.
Non-residually finite groups, okay.
Yes, so we see that, I mean, even the first one is hard to get in the cubulated setting, right? Because of what we heard from Danny about special cube complexes. And yeah, and the just infinite part, I'm going to use a lot of black boxes. I'm not going to prove everything in this lecture, but just tell you a story about how to construct such things. Okay, so let's get into the business. So the groups we're going to construct are going to be acting on products of trees. Okay, so let's denote by Tm the M regular tree. Oops. And for me, Avi said that the M regular rooted tree is the M regular rooted tree. So the M regular tree is the M regular tree. It's not rooted, okay? So for instance, T3 is this guy on the right. Okay, and infinite, right? No leaves. And yeah, so here's a definition of a collection of subgroups that we'd be interested in. There are BMW groups, so Bourier-Moses-Wise groups. And those are groups in the automorphism of a product of two regular trees that act simply transitively on the vertices of the product. And maybe I should say, I'm looking at the automorphism group of the product of two trees. If they have the same regularity, possibly I have an automorphism that reverses that, just to ignore those. They're not there. Okay, so it's really aught Tm times aught of Tn, if you want. Okay, and acting simply transitively means vertex transitive, okay? So I can take any vertex to any vertex, and simply means that I can do it in a unique way. Okay, so free action, which is transitive. Okay. Yeah, so how does one construct BMWs? It turns out to be an easy task. One can describe those quite nicely in a combinatorial fashion, and the reason behind it, in my opinion, is that the product of two trees is the unique cat-zero cube complex with the link at each vertex. Well, one has to do a slight computation. So it is the complete bipartite graph on M and N vertices. Okay, so the link in one tree is just a disjoint collection of M vertices and the other N, and you connect all of them because you take a product. Okay, and maybe, use this opportunity to advertise my own results. So there is a general thing there that you can say. So you can characterize when a link type gives you a unique cat-zero cube complex with that link. So we look at cat-zero cube complexes where the link at each vertex is some graph L, and we ask how many such things. So you have a unique such thing if L is symmetric enough. Okay. The condition I called super star transitive. Okay, which in particular means star transitive. Like you can take the star of any vertex to the star of any other vertex by an automorphism of L.
Wait, but the left regularity and right regularity are not the same.
Ah, yes, good. You can take, that's a very good comment. You see, I don't even remember my own definitions. So star transitivity means you can take any vertex whose star is isomorphic to the star of another vertex by an automorphism. That's
so in some sense, okay.
Yeah, anyway, but if L is symmetric enough, and believe me that.
I have a question about your result. Existence is clear, like the uniqueness is the problem, existence is clear?
So existence, yes. So this, I mean, okay, both directions require, I mean, there's some work in both, but what is clear is that there exists a complex with any given link.
Yeah, that's my question. That is true,
that's
independent of the choice of the link. That is just true.
Yes, this is just true, and it's called the Davis complex. Maybe at the end of the talk I'll get to that.
But if you're a complex with every link, then this assumption that you're going to get
Uniqueness.
Is to get uniqueness. So the existence of a complex with a given link type, this can be done generally using the Davis complex of the right-angle Coxeter group of this link. And uniqueness. For uniqueness, you need that. And I mean, the reason I'm mentioning this fact is that what we'll actually build is something, we'll build the quotient of the complex by the group, and we'll do it by, I mean, we need to make sure that the one vertex that's in this quotient has the right link. And once we achieve that, we know that the universal cover, or the complex that that's sitting there and we had to quotient by the group, is in fact the product of two trees. It's a local condition and one needs to check, and you get this global condition. Yeah, any questions about that?
Like the statement in parentheses, you mean there is a unique zero cube complex whose vertex is L if and only if L. What do you mean X is and P?
Yeah, okay. Yeah, good. Thanks. Okay, so here's a recipe. It gives you, I mean, it doesn't give all possible BMWs, but gives what we call involutive BMWs. So take the complete bipartite graph. Now we know where it comes from. It's supposed to be the link of the vertex. And choose a partition of the edges of this graph into 4 cycles. Okay? And the 4 cycles can be, so here's an instance of such a thing. So maybe this green 4 cycle is in my collection, but note that the 4 cycles can also be degenerate. So maybe something like this is a 4 cycle for me. That's fine. Also, just an edge is a 4 cycle, which also like shows you the abundance of, like, you can just, in a greedy way, just decide how to do it and then fill in the blanks with one edges if you need. Okay, and then what do you do with that? You define a group. So that's going to be our BMW group. And like in Amir's talks, this is going to be generated by some sort of like reflections. They're going to be involutions. So AI squared and or the BJ squared are 1. Okay, so those are the relations I'm adding. And now I want some kind of relations between A's and B's. And the relations between A's and B's are exactly going to come from the partitions that I have. So for instance, here I have this green 4 cycle in the partition. It will give me the relation A1, B1, A2, B2 equals 1. Okay, and note that the order doesn't really matter because they are all involutions. And okay, so of course this is only one of them. You do it for every 4 cycle in your list, in your partition. Okay. And then what do you do? Well, you can really construct the product of trees with a natural G action on it by just taking the Cayley graph of G with respect to this generating set. Okay, and add plus squares whenever they appear. For every relation, or whenever they appear, it doesn't matter. Okay.
What do you mean whenever they appear?
So whenever you see a square in the one skeleton, glue a square, an actual square. Note here that, okay, I'm slightly lying. When you take a Cayley graph, you'll have like two edges for A, but A is equal to A inverse. You get a bigon. So just I'm thinking of this bigon as one edge. Yeah. So sort of the simple graph. Yeah. Anyway, so yeah, so you get something that one can easily check that is simply connected, and the link at each vertex is the complete bipartite just by the construction, and so it's a product of trees, and naturally has a group action on it because it's just the Cayley graph of the group. Okay. Yeah, so this shows that G lives in this product of automorphism groups. No, so I'm saying something different. I'm saying take the thing on the right, okay? It's some square complex, right? Check that the link is a complete bipartite, and that the whole thing is simply connected. So you know it's the unique gets you.
Okay, so you
And
are
so it's
getting the
TM2.
effect from before, it's not like that. It shouldn't be obvious to me.
Let me connect it to milli machines. So milli machines are just automatas that have output. They read a letter and they output immediately a letter. Okay, and here, in fact, there are two milli machines hiding in, or many milli machines that are hiding. But how to interpret this as a milli machine? So you can think of the, let's say, A's as the states of your milli machine. Okay, and the BI as the alphabet of your reading, of the input, okay? And what does it output? So whenever it reads, whenever at AI you read BI, you output BJ exactly when BI is in a relation with BI and BJ are in relation with AI, okay? So there's some AJ somewhere. And that's exactly the state to which you arrive. Okay? So this gives a milli machine. And what's the connection between this milli machine and our product of trees? So in fact, you can read the action of AI, it's an element of my group, on the tree corresponding to the B's. So let's say A was in Tm, so I'm looking at the action on the tree Tn, okay? And the action on the tree Tn would be exactly the action given by this milli machine on the tree of words in BI. Okay, so for instance, I want to know, so I'm looking at the tree Tn, okay? And I have here, so there's a vertex, a fixed vertex corresponding to the identity element, sort of, that is fixed by A, let's say A1, just for the sake of and I want to know what it does to a certain path in the tree, or a vertex in the tree. So I'll read a word here. So there's some B1, B3, B something, whatever. Okay, and to know where this is sent, I'll just apply the milli machine starting at A1, the state A1, and see what the output. So let me depict it with squares by saying, okay, I'm applying A1. Okay, so here I'll get the output corresponding to A1. So it's something, I don't know. Okay, and I get to a new state, maybe A2, and I output the second thing, and so on and so forth. And this label that I see on top would tell me where to send the path B1 up to B something. Okay? Slightly lying, but let's say that this is what it is. And now I want to know what a general element generated by AI does. I just compose them, okay, and sort of build the bigger grid, okay, or just apply the Mealy machine one after that. Okay, let's see how to use this observation. Yes, so I can start at any state. This is like choosing the element that I want to apply, right? And from that.
Okay, when you show the runs of all these machines, so that you can combine them in this.
Exactly. So the height here is like performing A1 first, and then starting at a different state, doing A2. Exactly. And you see, of course, there's the sort of dual Mealy machine that has alphabet A's and has states B. Okay, so some again here. Those are not general Mealy machines, but it's called bi-reversible Mealy machines. Okay, good. So let's use it to build non-residually finite BMWs, following Danny's PhD thesis. So I have a BMW, and let me assume that it's irreducible. So irreducible means, let's just take the definition that would be convenient to us, which is if you look at the action of the group A, generated by the A1 up to AM, on the tree Tn, it has an infinite image. Okay, so a projection of A to out of Tn has infinite image. Good. Okay, so this is irreducibility for us. Okay. Then what I claim is that A, this group, is non-separable. Non-separable means it's not the intersection of the finite index subgroups that contain it. Or let's phrase it slightly differently. So here I want to say there exists an element, G, outside A, such that in any finite quotient of G, phi of G will belong to phi of A. So in the finite quotients, I cannot separate it from the image of A. It turns out to be the same as what I said before about intersecting finite index subgroups. I'm just saying there exists one element that you cannot separate from A. Okay, what is this element? It's exactly like in the intersection of all the finite index subgroups that contain A, but is not equal to A. Is not in A. Are we happy with non-separability? Okay. So yeah, let's see that. So let's first prove that among those elements, products of two generators, Bi, Bj, for different I and j, in any finite quotient, I can find one of them that's not separated. Okay? So we do it again. Take a finite quotient. I claim that there exists a pair I and j, different indices, so that phi of Bi, Bj is not equal, of course, belongs to the image of A.
But the quantifiers are the same?
No, okay, so there's still something to do afterwards, right? But it's a good start. Find some element. Okay. So yeah, so let's do that. So look at the kernel of phi intersection with A. Okay. The kernel of phi has finite index. A, we saw, has infinite image in OT of Tn. So what I claim is that there exists some element in this intersection such that the image, so the way alpha acts on the tree Tn is non-trivial. Okay, so it does something to Tn. Okay? But then what does it mean that it does something? Okay, so I can find some path that it takes to a different path, right? Some labeling that it takes to a different labeling. And let's break this labeling into the part of it that it takes to the same thing. So, I mean, this is supposed to be the bottom of this thing. So I'll break it into some long word eta, or maybe not long, that alpha would take to eta. And then the first instance, bi, where it takes it to something new, bj. Right? It acts non-trivial, so I can look at a path that it moves non-trivially and sort of think, what's the first time where I see some change? It could be that eta is trivial, yeah? Okay, so this is sort of applying the Mealy machine alpha on this path. So I apply it, I get to some state afterwards, or a word of states alpha prime. This alpha prime is also in A, right? It's in the alphabet A, so it's vertical here. And so I got a relation. Okay, and what is this relation? The relation reads that alpha, alpha and then eta bj is eta bi alpha prime. Okay? And now take the image of this thing in phi and see what happens. Okay, so take the image in under phi. Okay, so apply phi. What do you get? Alpha was in the kernel of phi, so it disappears. So I get eta bj equals eta bi alpha prime. Okay, eta vanishes. This equality happens in Q. Yeah. And I'm left with bj, or bi bj. There's an inverse, but they have order 2, equals alpha prime. And alpha prime is the image of something in A, right? Okay, so we proved this little claim. And now let's finish the proof. So as Gil said, there's a problem with the quantifiers, right? We want one element that works for all finite quotients and not an element for each finite quotient. But the key here is that the number of elements that we used is finite. Okay, so really what we can do is, if we assume that that for every alpha and j, I can find a quotient in which it's not in the image, then I can just build a new map that takes G into the product of all of those Qij's and does phi ij on each thing. And this is some finite quotient. And there I know that one of the ij's is sent to the image of A, which is, of course, a contradiction. Okay. Okay, so we got ourselves something that's non-separable, a subgroup that's non-separable. And here is another cool trick of Dani, is that you can now build a non-residually finite group by just taking a double of G along A. So what is this? I just take A1 up to AM, B1 up to Bn, and another copy B1 prime up to Bn prime. And I put all the relations that I sort of expect, right? Squared Bj squared Bj prime squared are 1. And I put the relations that I had originally, and the same relations but with a prime. And any combinations of okay. Okay, so this, so since A is non-separable, this turns out to be a non-residually finite BMW. And okay, I didn't plan on proving this, but it has to do with the fact that you have an automorphism that fixes A, the obvious automorphism that switches the two G's. Yeah, and separability is related to closed subgroups in some for finite topology, fixed points of automorphisms should be closed.
So
Okay.
this is true as long as A is not separable?
Yeah. Yeah, who needs assumptions, right? Okay. Good. So we got ourselves a non-residually finite BMW group, but now we want to upgrade it to a simple BMW group, or virtually simple BMW group. And for this we need just infinity. Okay. So here the history goes back to Margulis and the normal subgroup theorem, which showed just infinity to higher rank semi-simple groups with, say, trivial center. And Burger and Moses proved the version of it for the setting of product of trees, but nowadays there is a more general version of this that just works for in a quite general setting of product of two topological groups. So I'm going to say the assumptions, but I'm not going to explain them. I'm going to treat this whole thing as a black box somehow, and I apologize. So I have a subgroup in a product of two groups. I mean, think for us, in our setting, those groups are going to sit inside out of Tm and out of Tn, but in fact, they're not going to be equal. They're just going to sit inside this thing, and I'll explain why in a second. Okay? But we are naturally in a situation where when we have a group, the BMW, sitting in a product of two groups, and the assumptions are, let's say, I mean, the assumptions could be relaxed, but let's say GIs are simple, and we ask G to be what's called a co-compact lattice inside this product of locally compact second countable non-discrete groups with dense image. Okay? So what I'm hiding under the rug is that G1 and G2 have topology. They're not just groups, they're topological groups. Okay? And when I have this discrete subgroup G inside this thing, I want also to assume that the quotient G1 times G2 mod G is compact. Okay, that's the first part of the sentence. And I want to assume that when I project G to G1 and to G2, I get something with a dense image. Okay? Yeah, then we get that G is just infinite. Yeah. So what are the remarks here? The remarks are, well, some of them I mentioned, which is that, I mean, this, well, proved by Margulis in a certain setting, and then Burger Moses in the setting of the BMWs. But this is based, what did I want to say? Based on showing that the quotient, so take a normal subgroup in G. So this is based on showing that this quotient is both amenable and has property T. So I think for my talks, that's the connection to expansion, is that we have property T, and we saw already that property T is related to expansion. And let me also mention that this is, in a sense, surprising, because we saw in several talks that if G has property T, so some big group has property T, then we can use this property T for all the quotients to build expanders. Okay? But here, this is not this setting, because in our setting, G doesn't have property T. So really, the surprise is that still the quotients have property T. Okay? And this is actually quite a general, I mean, okay, I'm not going to define those things, but amenable and probability T are sort of contradicting each other, and the only option is that G mod n is compact, or in this case, because it's discrete, finite. Okay, so that's sort of the scheme of the proof. Of course, the detail is in proving that it has probability and it's amenable. I'm not going to say anything about that. But yeah, the second thing I want to mention is that that quite generally, the groups that act on cat-zero cube complexes do not have property T. Okay, so one cannot just expect expansion out of the box, so to speak. So G does not have property T. This is a result of Niblo and Reeves. That, I mean, again, the general thing is that a group with property T, when it acts on a finite dimensional cat-zero cube complex, it actually fixes a point. So it's never interesting to look at property T in the setting of group acting on cat-zero cube complexes. Okay. Yeah, so we want to use this, but as I told you, we have to sort of identify what's the right groups to put there. So while it's true, so maybe let me add a third remark. Let's see if so a third remark is that OT TM is okay, simple. It's not simple, it's virtually simple. It has an index 2 subgroup, which is simple. So let me write that maybe. Has an index 2 simple subgroup. Okay, so it's not so bad in terms of the first assumption. Okay, so let's say GIs are simple. This we can maybe assume, but the problem really is with the dense projections. Okay, so OT will never have a finitely generated subgroup be dense inside OT. Okay, so the projection of our BMW, which is our discrete, finitely generated subgroup, will never satisfy this with respect to OT-TM. So we need to come up with something else. This is, by the way, a result of TITS. The reason is parities. Like you can have, if you look at the stabilizer of a vertex, that's some countable group. And now you look at sort of the parities of how it acts on the first sphere, the second sphere, and so on. Those you can choose in whatever way you like in OT. So it's never going to be, you'll never find something that's countable and dense. So Burger and Moses solved this problem by introducing a subgroup of OT called the universal group on alt. So, I mean, they define it more generally, but let's give one instance that's relevant for us. So take a proper M coloring of the edges of TM, okay? And this gives you a way of relating the neighbors of a given vertex with the neighbors of another vertex, right? So for every automorphism of TM, I can now consider what kind of permutation it induces on the colors from like on the neighbors of V to the neighbors of GV. Okay, so what do I want to say? I want to say that for all V, we'll assume that G induces a permutation in alt M, okay, so the alternating group, on the, let's say, colors of the neighbors or the edges incident to V and GV. Okay, so for instance, I made this picture to make it a bit more clear. So I have some automorphism, let's say, that sends G to GV, and it takes this edge 1 to this edge, labeled 3. Okay, so I'll look at the permutation that sends 1 to 3. So what I'm asking is I want this permutation to be even, so exactly to rule out the parity issue that I talked about. And this turns out to be the right object to look at. So UM, so here's maybe a theorem that's, I mean, it follows basically from Tits that UM has an index 2 simple subgroup. Okay, so let's not worry too much about the difference between this UM and this index 2 subgroup. We can pass to this index 2 and not ruin anything for us. Okay, that's great. But now we still need to verify that the projections are dense, right? And this was the challenge. And this is what Burger and Moses did. So the theorem says as follows. So take a subgroup of UM. So think of this as being the projection of G to UM. Okay, and assume, so first of all, let's assume that M is at least 6. This is related to, we want alt of M minus 1 being simple. Okay, and let's assume two things about H. The first thing is that H is vertex transitive. Okay, note that I'm already assuming that H sits inside the universal group. So we know that locally H induces even permutations. But what we want is to assume that it actually achieves all of them. Okay, locally. So let's phrase it as follows. So let's look at the stabilizer of some vertex in H. It will hold for all of them by vertex transitivity. So really you can assume it about one vertex. And the assumption will be that when you restrict this to the ball of radius 2 around V, okay, so you see what it does to the ball of radius 2 around V, you want this to be the same as what U can do to the same ball. Okay, so all possible automorphisms that U induces, so the stabilizer of V in U induces on the ball of radius V also exist in H. Okay, so what we have here is a global condition, right, and a local condition. And what we get is a very strong global result, which is that that H is dense in UM. Okay. So what this means is that for our purpose of building a simple BMW, the only thing we have to do is guarantee that our BMWs will be vertex transitive by definition. BMWs are vertex transitive on the product of trees, obviously also on the projection to one of the trees. But what we need to check is that they satisfy this condition. So I get enough local behavior from H. Okay, and that's a very easy thing to do. So one can actually construct such examples. So let me just summarize this and then maybe discuss some more results. So how do you construct a BMW? So first you go to Danny. You ask him, give me a non-residually finite BMW. So find a non-residually finite BMW. Okay, on, let's say, M and N, okay, the regularities of the trees. And now just enlarge your sets M and N to some M prime M and N prime, and add enough relations to guarantee that locally you satisfy those conditions. Okay? That locally you see enough of those automorphisms. So enlarge the BMW. Okay, so now you take something that's bigger than to satisfy the local conditions. Let's see that we follow what we did. So we start with some BMW. Let me call it G0, and you enlarge it to get G. So it's not hard to check that G0 is actually a subgroup of G. Okay, I just added the relations. Maybe I killed some of the relations of G0. It doesn't happen. It sits as a subgroup. And so if G contains a non-residually finite subgroup, G itself is non-residually finite. Okay, and using Burger-Moses, we know that the projections of G to each one of the factors is dense in UM and UN. Okay, and so now you have non-residual finiteness and just infinity from the sort of normal subgroup theorem. Okay? Okay, let me mention maybe a result with Ivan Levkovich and Alex Margulis. We used exactly this to show that there are many BMWs. And somehow the reason is we saw how simple it is to build them. You just look at partitions of the complete bipartite graph, and then you need to maybe embed a little non-residual finite group in there, and somehow almost always the group that you will get will satisfy the local condition. Okay, so this gives you some enumeration on the number of simple BMWs. Maybe I'm lying. The BMWs are never simple. They only have finite index subgroup, which is simple. Yeah. Okay. So. Okay. Let me do that. They are virtually, I'll say virtually simple. Okay. So just meaning having finite index subgroup, which is simple. And in fact, you can even control the size of this finite index and show that in many of those examples, the index is 4. Okay. Which also shows a similar counting problem of BMWs up to commensurability, if you know what that is. But, okay. And also in that spirit, first when we thought about counting BMWs, we thought maybe we can use the probabilistic method. Just build BMWs at random and try and show that the random one is simple. The difficulty is actually the first one, just finding the non-residually finite BMW inside. But anyway, we built some random model, maybe just because none of us is a probabilist, so going to the most general thing. But the random model is the following. So you take n bigger, much bigger than, or not much, but bigger than m to the 5, and choose. So choose m. What do I want? M perfect matchings. Perfect matchings of this set n. Okay, so let me maybe give them. I forgot which was A was M. Okay, so maybe this will be A1. So one matching. I don't know at random. Yeah, I didn't say. And then here is another matching A2, etc., up to AM. Okay, and now build the partition by saying I'm connecting AI and AJ along BI and BJ if the matching match. Okay, so here, for instance, B, what is it, 3 and B4 match, and so I'll get A1, B3, A2, B4 as part of my partition. Okay, so that was the random model we used, and we showed that in this random model, when M and N go to infinity and this holds, you get just infinite subgroups, so they always satisfy the local condition, and hence they're also irreducible and so on. So I don't know, some fun little random model for BMWs. Yeah, okay. And maybe another last thing is a result of with a student, Michal Amir. So we build simple groups in products that are not trees, but a tree and some other guy, and this other guy is a Davis complex. So let me just tell you what this is. So you take a graph L, finite graph, okay, and you build the right-angled Coxeter group, WL. Okay, so let me tell you what this is. Note that it's going to be related to what Amir said, but exactly the opposite in a sense. So
The graph is the commutation.
yeah, exactly. So the graph is the commutation, and the non-edges are infinite relations, which Amir did not allow. So it's generated by the vertices of L, and I put the relation of reflection. I want it to be a Coxeter group, and V and W commute if and only if V and W is an edge. Okay, oops, that's not a set. It's a group. Sorry. Okay, and how do you build the Davis complex? You take you do a similar construction to what we talked about before. You take the Cayley graph, and you fill in squares, cubes, and etc. So build the Cayley graph, and glue cubes whenever you can to the one skeleton. Okay, so this is called the Davis complex of this game. So I don't know, XL maybe. Yeah. So what we did is we built examples of simple groups in such products where this L is the following graph. It's called the odd graph, and we saw it. We talked about the Peterson. You talked about the Peterson graph. So yeah, so the general construction is called odd graphs, or they're not as general as Kneser complexes, but they're just subfamily of Kneser complexes. You take the vertices to be all sets, and now I'm always getting this wrong. I think it's 2D minus 1. So D minus 1 subsets of the set of 2D minus 1 numbers, okay? And you connect two of them by an edge if and only if they are disjoint. Okay, so the case D is supposed to be the degree of this graph. Okay, so the case D equals 3, you get the Peterson graph. That's the only one I can draw. Okay, so what we did, we looked at this graph. You build the Davis complex of this graph. You plug it into this theorem, and as long as D is big enough and M is big enough, whatever, they have to be big enough, then you can actually build something that's simple. And I think I'll stop here. Thanks.